For some reason, this video didn't work the first time, so I'm just going to kind of go through this really quick. Okay, so we're going to talk about the natural numbers, whole numbers, integers. The natural numbers, if I was to ask you to count, you'd count 1, 2, 3, 4, 5. It comes natural to you. The whole numbers, just add 0 in there. The integers, you've got your negative whole numbers, 0, and your positive whole numbers. Okay, so it says use a plus sign, for example, for a positive. So we're going to talk about positive integers. If you do not see a plus in front of it, you're assuming it's positive. So it means positive. All right, so down here we were writing a negative integer that describes each of the following situation. A debt of $10, so it's a negative $10 or just negative 10. We've got a shore surrounding the Dead Sea is 1,312 feet below sea level, so below is negative 1312. A debt of $500 would be negative 500, and 280 feet below sea level is negative 282 feet. Then we graph things on a number line. I already have them graphed because I'd already started this video. So I put a dot at negative 3, 1 at 4, and 1 at 0. Okay, then I've graphed the negative 4 goes here, graphing 0, and then 3. Again, positive because you don't see a negative in front of it. Everything's positive. In order for it to be negative, you have to see the negative. Then we're going to talk about natural numbers, okay, and whole numbers. We've already done this, numerator, denominator. So basically a rational number is a set of all numbers that can be expressed in the form of a over b. Okay, b can't be 0. So we had 1/2, so a was 1, b was 2. We had negative 3/4, a was negative 3, b was 4, and for 5 I put a 1 under it. It still can be written in the form of a over b, where a is 5 and b is 1. When you're going to switch this to an improper fraction, you ignore the actually just bring the negative over, and then you're going to say 4 times 2 is 8 plus 3 is 11 over 4. So it's just, you're not going to deal with this, you're just going to bring it over and you're going to treat this like you did before. Then, in order to graph this, you would have to rather change it to a mixed numeral or a decimal. I changed it, it's 3.5 or 3.5. So that falls between a positive 3 and a positive 4, right smack in the middle. So I went over here between 3 and 4 and put a dot or a point in the middle. Negative 4.6 is between negative 4 and negative 5, but it's a little bit closer to negative 5. It's just past halfway. Right here I changed to a mixed numeral, so it was 4.5. That's going to be right smack in the middle between 4 and 5. Here's 4, here's 5, so I put my point in the middle. And negative 1.2, that's going to be between negative 1 and negative 2, but it's going to be closer to negative 1. Okay, then this is where, for whatever reason, my computer started glitching on it. So I'm just going to leave these because you can come back, because I wasn't going to do these, so now I'll do this one. So in order to change this to a decimal, we're going to take this rational number and change it to a decimal. So we're going to put 3 on the inside and we're going to divide it by 8. But 8 won't fit into 3. So we've got to put a decimal and put some zeros. I don't care, you can put as many zeros as you want. I'm just going to put 2 for now. So I'm going to bring that decimal straight up, and now I'm going to ignore the decimal down here. I'm going to say 8 goes into 30 3 times. I get 24. Subtracting get 6. I'm now going to bring down that 0. 8 goes into 67 times. I get 56. Subtracting get 4. I don't have a pattern, so it's not repeating yet. So bring down another 0. Oh, well, 8 goes into 40 5 times. 8 times 5 is 40, and we're done. Okay, so this can be written as 0.375. Now again, I don't care if you just have 0.375, I'm fine with that. Right here, we're going to take 5 and we're going to divide it by 11. Going to put 0.0. Okay, I'm going to bring that decimal straight up. 11 goes into 50 4 times. You get 44. Subtract and get 6. Add a 0 and drop it. 11 goes into 65 times. You get 55. Subtract and get 4. Okay. Now we're going to add a 0 and drop it. Oops, let's try this again. That upper level math got me. 60 minus 55 gives me 5, not 4. About messed up. Bring down your 0. Now at this point you'll notice that it's just going to repeat, but maybe you didn't notice and go 44. Subtract and get 6. Add a 0 and drop it. And it's going to go 5, and now you really can get 55 and you get 5, and you can really tell that it's repeating. So for this section it is going to be 0.45 with a repeating bar over the 5. Once we get out of this section we will not deal with repeating bars. Okay? Alright, so that way you can take a look at this. Alright, so we've dealt with rational. Now we're going to talk about irrational. Basically, rational numbers, I think that's what that says, rational numbers can be expressed as a terminating or a repeating decimal, just like here. Here's a terminating, meaning it ended, and here it was a repeating decimal. Basically, it's numbers or decimals that we're used to seeing, okay? Irrational numbers, I call them, irrational people are crazy. So these are crazy decimals. Okay? Just think about the people who are irrational. They go off on no reason, okay? They're crazy. So irrational numbers are crazy decimal, like pi. This is what it looks like, okay? Other irrational numbers include the square root of 2, because 2 is not a perfect square. Square root of 3. Square root of 25 is 5, so this one is rational. Okay? Where these are irrational. I don't know what they are, so, and I know we're not supposed to use our calculator on this section, but if we put in the square root of 2, the decimal runs off. It doesn't repeat itself, and it doesn't end. Square root of 3. Same thing. Now, the square root of, let's say, 36, that's a rational number. We're used to seeing this, so that's rational. These are crazy decimal, they're irrational. Okay, so the whole number system, the real number system, is made up of irrational and rational, okay, numbers. Now, there are other numbers that make it up, like the rational numbers are your natural numbers, your whole numbers, and your integers, okay? So, and here's some examples. All right, so I'm going to do this example right here. It says, consider this set. By the way, these squiggly brackets are called braces. List the numbers in the set that are natural, whole numbers, integers, rational, irrational, and real. Now they can fit in a couple different places, okay? Remember, natural are your counting numbers. So if I asked you to count, you'd go 1, 2, 3, 4, 5, okay? Whole numbers is everything, your counting numbers plus zeros, okay? Integers are negative, 0, and positive numbers. And then we just went over rational or irrational, okay? All of these, every single one of them, makes up the real number system, okay? Each one of these will be listed here. So let's talk about negative 7. That is an integer. Okay. It is also a rational number because we're used to seeing it. Because it can be written as -7/1. And it is a real number because everything's going to be in there. Let's make these sets so they're going to have braces around them. Okay. -3/4. It's not an integer because integers are whole numbers. It is a rational number. Because if you change that to a decimal, okay, it would be -0.75. We're used to seeing that. It's also part of the real numbers because, again, all of these are going to be listed. Now, 0. That's not a natural number. We don't count with 0 usually, but it is a whole number. It is an integer. It is a rational number because you can put 0 divided by 1. And of course, it's a real number. 0.6 repeating. It's not any of these. Okay. It's something that we're used to seeing. We've seen it a lot. So it's rational. And of course, it's real. Square root of 5. It's a crazy decimal. It doesn't repeat and it doesn't terminate. So it is an irrational number. But it's also a real number. Because remember, real numbers are all of these. Okay, pi. We already discussed that. If we did pi on your calculator, it gives you a crazy decimal. So it is irrational and real. 7.3. It's none of these, okay? But it's something that we're used to seeing. So that's irrational. And of course, real. And the last one, we can rewrite the square root of 81 as 9. Okay? Oops. 9 times 9 gives us 81. So that is a counting number. It's also a whole number. It's also an integer. My braces are getting worse up here. By the way, if you can't do these braces, you can just do this. Okay, I'm good with that. It's a rational number. It's something that we're, oops, you know what I should be doing? I shouldn't put 9. I need to put the square root of 81 on all of these. Got carried away because it should be these that are listed. So it was rational and it's a real. And so all we got to do is finish up our braces. Okay, I'm not doing this one. That one takes too long. Okay, ordering. Notice that we have our negatives, 0 and 1. Okay, 2 is less than 5. Sorry, this is blurry. It's not the video, it's the actual copy. Okay, because 2 is to the left of 5. All the numbers to the left are less than the numbers. Okay, so the ones on the right are going to be the higher one. So, and by the way, this is a less than symbol. This is greater than. Okay, you can make a less than symbol with your left hand. So, 3 is less than 17. So it goes like that. And I think of it as money also. You have $3, someone else has 17. God, why do I keep saying 15? So it's less than. All negatives are less than positives. Negative 4.5 is down here and 1.2 is right here, so it's to the left. Negative 5 is here. Negative 83 would be way down here. So negative 83 is smaller than that. So negative 5 is greater than. Now, to me, it is easier if you change these to decimals. This is 0.8. This is 0.6 repeating. Okay? Think of money. This is 80 cents, 66 cents, 67 cents. Okay? Okay? Same thing with here. It's better to owe somebody $5 than owe them $83. Okay. And the last page of this, we also have less than or equal to and greater than or equal to. Determine whether the inequality is true. Okay, so only one of these has to be true in order for the whole thing. So is -7 less than 4? Yes, so it is true. -7 is not less than -7, but it is equal to it. So this is true. -9 is greater than -6. No. -9 is equal to 6. No. So this is false. Right here, -2 is to the left of 3 on the number line. So this is true. -2 is equal to -2, so it's true. But -4 is not greater than 1. See, -4 is here, 1 is here. It's to the left, so it's less than. So this one's false. And the last part that we're going to talk about is absolute value. Absolute value is denoted by these two straight lines. It's the distance from 0. Okay, so distances are never, they are always positive. They're never negative. Okay, so if you were talking about the distance from 0, where is -5, okay, it's going to be 5 steps away from 0. The absolute value of 5 is 5. Right here, the distance from 0 that -3 is 3. Okay, 1, 2, 3. Doesn't matter whether it's left or right, it's just the distance from 0. This is 6. The distance from 0 to 0 is 0. Right here, the absolute value of -4 is 4. Absolute value of 17 is 17. And the absolute value of a negative square root of 2 is the square root of 2. And that finishes up 1.3.